that looking okay for you?
Yeah, looks great. Thank you.
Good. Okay, so you want me to get started?
Yep, go ahead.
Great. Okay, good. Well, thanks everybody for coming. Today what I'm going to talk about is some advanced methods for user evaluation in AR and VR studies. But I want to start, first of all, with a bit of history and talk about some old user studies that I did and lessons learned from that, and then talk about some more recent work. So first of all, when I first started doing VR, we were using systems like this. So this is a desktop VR system from 1995. It was very expensive, so maybe $150,000 to $250,000, depending on your setup. And compared to today's technology, of course, very limited, only 2 million polygons a second, and just a VGA resolution head-mount display with relatively low frame rate. And you can see on the bottom left there, the type of graphics that we were getting. But around this time, I conducted my first published user study. And so I want to talk about that and some lessons that I learned from that. So my first published experiment was in 1995. And this experiment was to explore if people can draw sketch maps to measure the cognitive map of virtual environments. So in geography, people have been doing sketching of maps for a long time, but nobody before had applied that to virtual reality. And so the hypothesis was that people who are better oriented in virtual reality will produce more accurate sketch maps. So we used that system I showed you before, and we had three very simple virtual environments. And it was a between subjects design. So each person experienced only one world. And we had a lot of people doing the experiment, almost 100. So we had between 24 and 35 people in each world. So you can see in the bottom right, one of the examples of the types of worlds that we were using. And so what we'd do in this experiment, we would train people in a simple world. This was the world we trained them in. This is a virtual model of Seattle. Then they would complete a survey about spatial perception and presence. Then they would go into a test world, then they'll produce a map, and then complete that same survey again. So this allowed us to conduct several types of measures in the experiment. One was that we had all these physical maps that were being drawn. So we wanted to be able to analyze the maps in terms of how accurate they were, if people got most of the types of objects, if objects were positioned relative to each other. We also had a subjective survey that was 24 questions, and you can see on the right-hand side some of the questions. So one of the questions, for example, was your sense of being there between none and total, your ease of interaction between impossible to effortless. So people answered that on a scale of 1 to 10, and then we have subjective comments. So this is some example results. The blue square there shows an example of one of the virtual worlds that we had. This is called Cloudlands. It was supposed to be a virtual world that's all in the clouds. Very simple graphics, obviously. And on the right-hand side are some of the sketches drawn from this. You can see one person's drawn a kind of a 3D sketch, other person's drawn a top-down view, and the other person's drawn a kind of a front view. And people were told to produce a map of the world that someone in familiar with the world could use to navigate around it. And here's some results we found. Basically, what we found is we asked people how oriented they felt in the virtual world and how much they felt if they knew where everything was. And you can see that on the bar charts there. And we found a correlation between that and how good the map was, and also how correctly oriented objects were in the map and placed in the map. And there was also a significant difference between the subjects understanding where everything was and in placement of objects, and also in their sense of dizziness. So that was a very first study. There was some positive lessons learned from that. One was that I used a mixture of subjective and objective measures, which was good. I also used some existing measures from other domains. So there, as I said before, there's been a lot of work done in geography with sketching, but almost nothing in VR. At that point, nothing in VR. And so I was able to look at this geography literature and use some measures they used. And I also created my own experiment measures. But there's a lot of mistakes that I made, and now, looking in hindsight, I was actually very surprised that the publication was able to get published. For example, we had people draw maps, but there was no spatial ability task to measure people actually had good spatial ability. The Likert scales weren't balanced. So if you go back to here, you can see the Likert scales going from impossible to effortless. Those semantic words at the end have, those words at the end have different semantic meanings. So not very balanced Likert scales. The experimental measures was very simple. The statistical analysis was terrible, and actually there was some missing data as well. And I didn't even record the subject demographics, how many men and women and what their age was. So I'll be very surprised if that type of experiment got published today. Following on from that, I started doing more research in collaborative AR systems, where my PhD was. And so we developed one of the first world's first collaborative AR VR experiences with see-through AR displays. And the goal of this experiment was to see if seeing the other person's body would help you perform a task better. So you can see two of us there, very young, skinny version of me. And then for the experiment task, when people put the headset on, they would see a target object in front of them. They have to select the object and put it into these wireframe boxes. So you can see here this white cube, and they'd have to select that object and place it inside the white frame. And apologies for the black and white images, but all color pictures have long since gone. So it was a collaborative task. So one person had to find the objects, and then the other person, once they'd found them, they could make them visible to the other person. The other person had to move them. So it was there was role division. And there was two-factor design. There was, you either had a body or no body, or you had an AR VR condition. And you can see in the bottom right-hand side, that rectangle there with the cylinder or cone coming out of it, that was a person's very, very crude virtual body. So we had 5 conditions with 2 in the real world with a real body or with no body. In the real world with no body, we had a divider between people so they couldn't see each other. And in the virtual world, we had either virtual world without a body, and also we took one condition, we took the walls out. We thought the walls would be providing a distraction. And we had a within subjects design. We had a much better experiment design. So this point, I got the idea that Likert scales should have similar terms on both ends. So you can see the Likert scale on the right, and we also measured the performance time and the ranking of conditions that people like the best. So here's a snapshot of the results. We found that there was no significant performance difference in terms of time overall, but there was a significant difference between the real world and real body and the virtual environment, virtual body case. There's also a learning effect as well. So you can see the graphs on the right-hand side here showing the performance ranking, for example. People thought that seeing the people in the real world with a real body performed much better. And then we also had some subjective ranking, so they thought they could play better when the body was present. So some of the lessons I learned from that experiment was that it's a good idea to combine qualitative and quantitative measures. Performance time can be a very poor measure in a collaborative task, especially because as many factors can affect performance. And it's really important to use multiple subjective measures. So we had people fill out a Likert scale, but we also had them rank results as well, because people, of course, can answer the same number in a Likert scale for different conditions, but if you force them to rank, they can't. But I still made mistakes. There was no user interviews. I didn't think about learning effects. The statistical analysis was terrible, and I didn't make my own notes about user behavior. So this leads me to my third experiment that was done a year or two later, and this is also about collaborative and AR. And in this case, what we're looking at is there a difference between AR-based and screen-based face-to-face collaboration. So you can see a little sketch up there. You've got 2 people sitting around the table looking at AR objects on the table, and that means that the objects form a subset of the communication space. But if you're looking at a screen, then the task space is separate from the communication space, and you really can't see each other while you're looking at the screen. So the hypothesis was that being able to support face-to-face collaboration with AR would produce much more similar behaviors to face-to-face non-AR behaviors than screen-based collaboration. So we had this experiment design. You can see there's 3 conditions. The task was for people to arrange buildings in a 3x3 grid, and it was a puzzle. So there was a number of clues as to how to arrange the buildings. For example, you couldn't put the pub next to the church, or the school had to be across the street from the shop. But only each person only had half of those clues, so they had to talk to each other to explain what the clues were and solve the puzzle. So you can see three conditions: a face-to-face condition with a little cardboard buildings, a augmented reality condition where you pretty much had the same cards, but when you looked through the AI headset, you would see a virtual model of the same building appearing on the card, and then a projection condition where you're looking at the wall. And the key difference, as you can see from this, is that when people are looking at the wall in the projection condition, they can't easily see each other and the gestures they're making because they're side by side, whereas in the face-to-face and AR condition, they're across from each other so you can see each other. We had a range of quantitative and qualitative measures, and this time we used performance time again, but we used communication measures such as the number of types of gestures made, the deictic phrases spoken. Deictic phrases are things like "what is that?" How many terms spoken per phrase. We also had qualitative subjective survey, and we had an interview this time. So in terms of results, we found this time there was a significant difference between conditions. The AI was slowest, but there was interesting behaviors happening in the communication measures. In particular, people spoke the same in the face-to-face case as they did in the AR case, but significantly different than they did in the side-by-side face-to-face or projection case. You can see, for example, this top bar chart here shows, or the bottom top bar chart here shows the percentage breakdown of the number of gestures made, and for example, the number of pointing gestures. And in the face-to-face and AR case, they both make about 40% on average, whereas in the projection case, the number of pointing gestures drops down to 30%. The number of picking or movement gestures goes up to about 65%. And we also asked people how similar it was to manipulate the content in each of the conditions, and people said that it's pretty much the same to manipulate the AR content as in the face-to-face, which is not surprising because they were manipulating the same cards, but much different and harder to use than with the projection case. So some of the lessons we learned, well, first of all, with a communication task like this, the process measures are really valuable, measuring speech and gesture. Also, it's important to get user feedback from interviews. For example, on the right-hand side, we've got some interesting insight. One person said that the AR's biggest limit was a lack of peripheral vision. People were using head-mount displays with very narrow field of view. And so one person said that it was like working solo together. You could sometimes see the person across the table, but other times you couldn't. We did a much better statistical analysis and we made some better observations. But again, there were some mistakes from the surveys and the interview analysis. So the last experiment I want to talk about is not one that I did, but one that was happening at the same time. It was done by the University of North Carolina, which is a really, really nice example of how you can combine different measures together in a study. So in this case, they were looking at presence, and this is a famous experiment called the pit room. They basically built a room that had a virtual room that simulated a drop into a pit, and you see that on the bottom right-hand side there. You've got two rooms, actually, a small entrance room, which was like a little living room, and you walk through the door, and then there was a narrow walkway around the wall, and then there's a two-story drop down to the bottom. And they built this in the physical space as well. So you can see at the top there, the person standing on the edge of some planks, and that provides the feeling of standing on the edge of that drop. They can wrap their toes around the edge of the planks. So there's some haptic feedback. And so they did several tasks. One of the tasks was to pick up objects and carry it across the pit, and then drop the virtual balls down to targets. You can see at the bottom the red and blue target. So that provided a strong sense of presence, because you could see this very strong feeling of depth as you're standing above the pit. So I'm not sure if any of you have been in experiences like that, but I want to show a little video of, and actually, I don't think let me stop my sharing and restart again to make sure that I can get the audio set, because I don't think I'm showing the sound. Okay, and I need to share this desktop here. So let's start that again. So hopefully you can see that okay. So I'm going to show you a video. This is not from this particular experiment, but from a similar experiment where people are walking across a pit.
That's so good! Oh my gosh. Wow, this really is crazy.
So you can see it's obviously very scary. It creates a very high sense of presence, and you'll see in a little bit some of the video of people, show behavior like this, where it's obviously they're very scared and they feel very much in the real world. So this is the world that they had. It was basically a VR environment with a narrow plank that was going between two doors. It was and a huge sense of depth across that drop there. So the interesting thing they're exploring with this experiment was measuring presence. And up until that time, people used a wide range of subjective measures, self-report measures of presence. But what they want to do is explore objective measures, and in particular measures that can be captured from physiological cues. So they measured the change in heart rate, the change in skin conductance, and also change in skin temperature. And they want to look to see if that would correlate with subjective measures around the well-known UCL presence questionnaire, which was a Likert scale questionnaire, especially focusing on behavioral presence. So they did 3 experiments in that room. One was looking at the effect of multiple exposures, another was looking at passive haptics. So you can see the person there standing on the board with their bare feet, and they're wrapping their toes around the corner of the board, so they really feel like they're on the edge of a precipice. But in that was the haptic condition, and they do another condition where they didn't have the boards at all, and you wouldn't feel that. And then the effective frame rate and what happens when you increase the frame rate from 10 to 30 frames a second. And in particular, they're looking at the presence correlation between subjective and physiological measures. This is what they found. You can see the bar chart there shows the change in heart rate in beats per minute when people are using the physical lead with no physical lead, so the heart rate went up. It also shows on the right the change in beats per minute with the frame rate. So again, the frame rate went up as well. So there was a significant change in heart rate in the haptics and frame rate experiments. With repeated exposure, there was decrease across all the scores. So the presence survey scores and the physiological scores all decreased, which is not surprising. But more interestingly, there was a really interesting correlation between heart rate and presence in the frame rate experiment, and between skin conductance and presence in the multi-exposure experiment. And that is because the frame rate experiment was one where people were dropping the balls down the pit. So it was the one that was the scariest. So there was a good correlation between heart rate and presence there. So the key lessons you can learn from this is that you can use physiological cues as a presence measure, and also as a process measure. So what I mean by process measure is you can actually capture them during the experiment. So the change in heart rate in this case is a possible objective measure of presence, especially in very high presence environments. And they also showed you can get an agreement between the subjective survey results and physiological cues. There's a lot more research to be done in this space. What type of other physiological cues you could use, how different subjects may have different responses, and correlation with other presence measures. And in fact, in I guess a couple of weeks, Aaron Day is going to report on another experiment which we've done more recently, looking at neurophysiological measures of presence. So continuing this kind of same experiment, but looking at a wider range of physiological cues. So that shows you some early results. I want to take a small detour and talk about user studies in general. And a couple of years ago, we published a review of 10 years of AR user studies. So this is a meta review of all these AR studies done in usability from 2005 to 2014. And so what we found, a couple of things. First of all, it turns out that in the augmented reality literature, there's actually very few papers that have user studies in them. You can see on the left-hand side, there's around, it's trending towards about 10% now of AR papers will have a user study. And then on the right-hand side, it talks about different types of displays used in those user studies. But that was quite surprising to us that amongst all the published papers, there's a relatively small number of user studies. In 2014, getting towards 1,500 AR papers, and just over 150 or so of them have a user study in them. And we also looked at different application areas and different experiment types. And you can see on the right-hand side the types of experiments. And by far, the largest type of experiment was formal user studies, that dark blue, followed by field studies to a minority. And then there's a bunch of pilot studies, and almost nobody's done any heuristic evaluations. And there's more data as well. So I won't go through all of this, but you can read the paper if you like. But basically looking at the types of studies people do, one interesting thing is that there's a pretty even split between studies that use head-mount displays and handheld displays. It also looks at the type of locations of the studies and the mean number of people in the studies and the study design, whether it's within subjects or between subjects. But overall, we found a number of interesting things. So first of all, most papers use within subject design. Most experiments occur in a controlled environment. Only around half of the papers report using both qualitative and quantitative measures. And as I showed with my old experiments, one of the things I learned pretty early on is it's really important to have both qualitative and quantitative measures. But by far the largest number of AR studies are using performance measures. Almost all the studies focus on visual sensors, and most of them were using university students as subjects, about 60%. A good split between head-mounted and handheld displays, and most studies are focused on interaction, and almost no user studies on collaboration. So, so that's a really interesting paper, and it shows you where we are right now with typical AR studies and where where's opportunities. One of the big opportunities identified this is on collaboration studies. So I want to talk now about some more recent work that I've done that are collaboration studies, and show some newer techniques we've used in those studies. So first of all, we wrote a paper a couple of years ago talking about using AR and VR to share communication cues between two people doing a collaboration task. So the basic idea was you had a person in the real world with an AR headset on, and they scanned their real environment and made a copy of it. And then a second person in VR in that environment helps them perform the task. So the VR person feels like they're standing in the same environment because they're in a virtual copy of the real world. And when the AR person looks around, they can see a virtual person standing beside them to help them with this task. But we're really interested in what we could do in terms of sharing communication cues, things like gaze and gesture and head pose and body position. So this is some of the communication cues we used. You can see on the bottom HoloLens AR display and HTC Vive. Both of them had leap motions on them for gesture tracking. And then the people were represented as these kind of very crude avatars with two hands. But then one of the interesting communication cues we're looking at is showing gaze and head pointing direction. So of course in a face-to-face collaboration, you can only see where the other person's looking when you can see their face. But with AR and VR, you can provide additional communication cues. So our idea was to provide a view frustum. You can see in number C there. And so when the person is looking around and can't see the face of the other user now, they can still see where they're looking by using this view frustum. And then there are other cues you can provide as well. So D shows a head pointing ray, that blue line, and E shows eye tracking and using an eye gaze array. So that the hypothesis was that not only would you want to know where the person was looking, you want, well, where their head is facing, you want to know where they're actually looking as well. So that was the setup in terms of the communication cues. And we had these four conditions. So in the baseline condition, there was only heads and hands. We had a field of view condition where you only showed the field of view of each person. Then you had a condition showing the head gaze ray and the eye gaze ray. So it's pretty much B, C, D, and E in this chart here. So the baseline with no additional communication cues. And then the other three that had some field of view representation. And the hypothesis was that the baseline condition would be the worst, providing the head gaze and eye gaze should enable people to perform better, and the head gaze and eye gaze will be more preferred. The baseline condition may require more movement because they need to look at the other person's avatar, and it may be more distance separating the people so they could see the avatar. In terms of the task, we had a search task, and people had to look around and see these virtual cubes floating in space, and the cubes had numbers or letters on them. So one person saw letters, the other person saw numbers, and what they had to do, they were told to find a cube with a certain number-letter combination. So they had to communicate with each other. So that in this case, for example, that might be looking for the cube G3. So one person would see the number G or letter G, and the other person would see the number 3. Then they have to talk to each other to make sure that they're on the same cube. And once they've found the cube, somebody had to pick it up and put it into a place where that blue donut is. So it was, again, a task separation collaboration task. So here's shows some people doing that task, and you can see the pink pyramid appears there showing the view frustum of the other person. So let me show a little video. First of all, you'll see the copy of the environment, and then this is the AR view. So this is my collaborator looking at me. I can see the pink view frustum and also the green line, which is the eye tracking. This is now me looking in the VR case. So now I can see the pink view frustum of my collaborator next to me, and we found the cube successfully, so it turns green, and they drop it into this little donut here. So you can see us performing the task there as well. So you had to collaborate with the person, and the pointing and head view frustum cues were very helpful in performing the task. And people were both in the same room, separated by dividers, so they could talk to each other. So that's the experiment. In terms of performance measures, we had some performance measures around task completion time and rate of mutual gaze. We also looked at behaviors that people observed, number of hand gestures they made, how people moved, and then a number of subjective surveys. And one of the things we did in this case, which is really important, is I learned again from my past, and I actually used some validated measures of usability and social presence. So things like the system usability scale for usability. And we collected data from 16 pairs of people, 9 women, and some experienced and some not experienced. We had 4 conditions with 8 trials per condition, so we got 512 data points of objective measures, and then subjective measures we had 128 because less surveys. So here's some of the results that we found. You can see the subjective usability scale on the top there, the social presence scores on the bottom, and scores around co-presence and gesture use on the bottom as well. And the yellow lines show the significant differences. I won't go into depth because the main point is to show you that we use a bunch of experiment measures, not to go around the results of the experiment. One of the interesting measures we used, though, was looking at motion data. And so you can see here a heat map showing how people moved around. And then you could calculate the area of the heat map to see how much they moved. So for example, in the baseline condition, the AR circle is quite small, and the VR circle is much bigger, about 50% larger area, showing that the person in VR walked around more than the person in AR did. So the basic results was that we found that there was no performance difference. However, there was so there's no difference in task completion time, but there was a significant difference in ease of use scores, and people overwhelmingly felt that being able to have those communication cues, whereas a view pyramid or the gaze rays, helped a lot better than just having the baseline condition. And we also found that when we had those communication cues, the amount of gestures used decreased significantly as well. So you can see on the bottom chart there, the baseline condition, those bars there show how many gestures people made. And as you're across the conditions, you can see a drop. For example, the head gaze, the blue pointing is much lower than in the baseline condition. So I just want to talk about three last experiments, actually. So one of the important things I learned from that experiment is the importance of communication cues and capturing these process measures, in that case, movement body. But I also wanted to look at how we could use new types of physiological sensors as well. So in the recent years, we've started looking at using more EEG in our experiments. So in 2019, we did this experiment on looking at using EEG for adaptive VR training. So people have used the EEG a lot in VR, but mostly it's used for brain control interfaces where you concentrate and you select an object on the screen, or menu item or something like that. But what we want to look at is look at if we can use EEG to monitor cognitive load, and then to use that to build adaptive VR training systems. So the basic idea is that when you're doing training, if your brain is working really hard, this is a heavy cognitive load, you may want to change the training experience to make it easier or harder to better train the person. So as I said, there are a number of current VR training systems that people have developed, but in many cases, they're just like using effectively PowerPoint in VR. We have a step-by-step methodology to go through, and they don't measure people's cognitive load and adapt to them. And there have also already been a number of experiments prior to this showing that you can actually measure cognitive load from EEG, and there's a whole decades of experience in psychology, but nobody had really applied that to VR before. So we built a system like this. It's basically a brain products EEG cap that the person wears at the same time with the VR headset. Very difficult to get them to work at the same time, but We managed to do that. And then we had a very simple Unity VR experience. And we also had some processing of the EEG data that went on between the trials to measure the cognitive load of the person and to adapt to the trial. So first of all, we had to measure people's innate cognitive ability. And so what we did is use what's called an in-back task, which is that basically you have to memorize numbers and recall if a number being shown to you is similar to a number that was shown one or two numbers before. And that's been shown in psychology to be a very good measure of people's cognitive ability and cognitive load ability. And so we measured the alpha brain activity. So that's basically task load. And that enabled us to set a baseline. And then in the experiment task, the idea was to try and increase the complexity of the VR system to increase the cognitive load. And when the cognitive load exceeded the baseline measure, so exceeded your capacity, then we'll try and decrease that level of cognitive load. And if it was below the baseline, we'll try and increase the level of cognitive load. And this was to simulate a training example. You can imagine a VR training, if it's very, very simple, then a person may not learn very fast. So if we are able to measure that the person is having a very simple training experience, we could dramatically increase the cognitive load or complexity of that training experience to get to the point where they're training at an optimal level. And conversely, if it's too hard, you might give up and again not learn. So once we got above the baseline cognitive load level, we decreased the complexity down. So this is the experimental task we used. It was a very simple task. Basically, inside the VR environment, you would see in the corner of your VR headset a pink square, and inside the pink square there was an object, and you had to look around the environment to find that object, and then put the red reticle on the object and pull the trigger on the VR headset. So very simple. You can see on the left pane there, the person's looking for a yellow ball, and the yellow ball's right in front of them. But then what we did is we increased the complexity of the task, and we had 20 levels of complexity. And as we went up, then you'd get more objects in the scene. The objects would start occluding each other. Some of the objects would start moving. That'll be a different size. And so it actually got quite challenging at the end point. And so the target selection got more and more difficult. You can see this task load level on the right-hand side is showing 40.9 compared to 11 on the left-hand side, because there's more objects and they're spread all around the person. So here's some videos. The left video first shows the low level difficulty. The person's looking for a green ball, very easy because there's really only 4 or 5 objects in the scene. So it's super easy. And then this is a high level of complexity. So now they're trying to find a red ball again. There's one there, a green cube, but some of the cubes are disappearing behind others. And so you can't find this yellow square. There it is there. So this is a much higher level of difficulty on the right-hand side. So we had 14 subjects. They didn't have any experience in VR. We would measure their response time and also measure their brain activity. This is used calculated by the alpha power from the raw EEG data. And people did the task for 5 minutes, and each, I think it was 30-second trials. I can't remember how long the trial was, but after each 30-second trial, we would stop and we would calculate the alpha power, and then we would change the complexity of the trial for the next one and keep on going. So this is the basic how it would go. So you can see here time along the bottom going up to 5 minutes. And then when the person first starts, the baseline alpha power level is 3. And this dotted line here represents their cognitive load capacity. So the goal is to, as quickly as possible, increase the cognitive load up to this level. And when you get to this level, just keep it at that level. So you can see it hits 15, it goes to 16, and that's too high. So then it drops down to 15 again, and it goes up again and down again, up again, down again. So, and then we hypothesize that this level here is where you get peak training. So it looks like for almost, I guess, 100 seconds of the time they're at peak cognitive load training level. So we did that, and then what we found, first of all, in response time, we found actually there was no difference in people's response across the different complexity levels. There was 3 levels of complexity, like I said, and the average response time was, well, it was about 3 seconds or so, 2.5 to 3 seconds. You can see there's kind of a trend down, but those error bars shows a very wide variance, so it wasn't a significant difference. What we did find, though, was significantly higher brain activity. So you can see the left pane here. This shows the brain activity at different frequencies of the alpha channel in the brain. So around 0.5, you've got this yellow activity happening here. But on the hardest levels, you can see a lot more brain activity happening around the 0.5, 0.6 level over wider range of frequencies. And so here's the difference here. So we found that indeed increasing the cognitive load did increase, or increase the difficulty did increase the cognitive load. But we also found that people increase their cognitive load to maintain and sustain the task performance. So people were working harder and they're performing just as well, but it required more brain activity. So in conclusion, from this experiment, what we found is that we can indeed build VR systems that increase the user's cognitive load without necessarily affecting task performance. This is the first demo of use of real-time EEG systems to adapt the complexity of a VR training environment. Of course, it's a very simple training task. So in the future, we want to be able to look at different tasks, and also so we're increasing task complexity. We're also quite interested in using AR displays and seeing what happens when you have a real-world visual behind the virtual content, and whether that provides distractors. So that was just using EEG by itself. The next experiment I want to talk about is how you can combine EEG with other sensors as well. And so this is an experiment we did around trust. So there are many examples of people using intelligent agents in their everyday life that they need to trust. For example, a self-driving car that is going to drive for you, or even your map and GPS on your mobile phone. And according to AAA, 70% of Americans are afraid to ride in a fully self-driving vehicle. So we want to look at, can we have some way to measure trust and then use that to adapt the system to us. So for example, if we are in a vehicle and we're not trusting what the vehicle is doing, maybe the car should talk to us and figure out why we don't trust it, or modify its behavior in some way to increase that level of trust. So people in the past have used a wide range of subjective measures to measure trust. And so the STS, the subjective trust scale, for example. What we want to look at is how we could then look at exploring how you could measure trust with physiological cues and how that correlated with those subjective measures. So in this case, we used brain activity, EEG again, the GSR and the heart rate variability. GSR is a sweat level on the skin. And we wanted to look at if there's a relationship between the cognitive load and trust. So we implemented a simple VR agent to help you perform a task better in virtual environments, and then compared all these physiological and behavioral and subjective measures together. And we actually used the same task as before, because we'd already shown that task can increase cognitive load. But what we made 2 changes. The first was that we implemented the MBAC task inside the VR environment. And the second is that we had a virtual agent that would provide voice guidance. So you're inside this VR environment and you'd hear this voice saying, turn left or turn right, to guide you to where the target was. But the thing is, the voice sometimes wasn't very reliable. So we had 2 factors. One was the cognitive load factor, whether it was an easy or a hard task. And the second was the accuracy of the agent. So you had, in one case, you had no virtual agent, so no voice cue. The second case, you had an agent that was 50% accurate, so half the time it would tell you what was right and half the time was wrong. And then the third case was a 100% accurate agent. And so that was designed to measure your trust. Presumably you wouldn't trust the agent that wasn't accurate as much as an agent that was accurate all the time. And of course, with no agent, you had no trust at all. So we measured, as I said, a bunch of physiological measures. So we measured the EEG, and we measured the alpha power again. We measured the GSR and heart rate variability. We measured the performance and some subjective measures. And so these are the results. We basically found that just like before, we were able to measure a significant difference in the alpha power level with the EEG. And then looking at the heart rate variability, we were able to see a significant difference in the finite Fourier transfer processing of the raw data corresponding to trust value. So you can see in the bottom here, the agent trustworthiness, and you can see that little peak there well, the red line, I should say, this is the line for the agent's 100% trustworthy, and the green line is the agent that is not trustworthy. And so you can see it's significantly higher at around 0.15 hertz. We also found that the performance was better with the more accurate agent, and there was also a significant difference in the subjective measures of trust as well. So this a little bit matches what was done with the presence survey I showed you before, where they had a correlation between a physiological cue and a presence score. In this case, we've got a correlation between a physiological cue and a trust score. So that implies that potentially in the future we could have virtual agents that measure our trust based on a physiological response and react to us. So the last thing I want to talk about was that some most recent work we're doing, and we're looking now at brain synchronization in VR. And so over the last 10 years, people have been doing some user studies on EEG and brain synchronization in real environments. You can see two people here sitting, where each of them wearing EEG brain caps, and they're each pointing at the other person's hand, and one person's going to start moving their finger around, and the second person's going to follow their finger. And this physical task has been shown to cause brain synchronization. What that means is that if you measure the electrical signal of the brain, then the phase of one person's brain activity will come in sync with the other person. So it's quite a remarkable phenomenon. And for certain physical tasks or other tasks, sometimes people's brain activity comes into phase. And when that happens, people report being more connected to the other person and feel like they collaborate together better. So this shows the brain activity of those two people before they start that finger pointing session. You can see the black dots there represent the EEG electrodes, and then the color heat map is the brain activity. So we have them doing that finger tracking task, and then they stop and hold their fingers still in space. So they're not moving anymore. And we measure their brain activity again, and we see something like this. So these arcs here show the electrodes which are in sync with each other. So you can see between those two people, there's a fair degree of brain synchronization. So that's been done in the real world, but nobody's done that before inside VR. So we decided we'll have a try in VR. So here's our VR setup. Of course, because people in VR, they don't need to look at each other anymore. So there's two people in the VR environment, and in the VR environment, they see this. So you can see an agent sitting across you, and then the agent starts moving their finger based on the motions of the real person, and then you have to map that onto them as well. So both people try and track each other's fingers again. But the really interesting thing, though, with VR is that you can jump into the other person's body. And so we also looked at what happens when you get into the same person's body. So here we are, two of us in the same body. And you look down, you can see two pairs of hands poking out. And again, you have to follow the other person's hand. And so we're still analyzing the data from this, but the early results are very promising. This picture here shows the brain, and the red spots are where the EEG electrodes are. These lines here represent electrodes that are in phase with each other, but there's very few connections. And this is before we start doing the training in the first person perspective. So this is basically noise data. But once we've done that VR experience in the first person perspective and the finger tracking, we get a result like this. And you can see those strong, dark red bands represent 4 or 6 connections between the electrodes, so much more connections. And so we think that, with VR, we can also produce brain synchronization. And there are some things about VR, like being able to be in another person's body, that could increase brain synchronization. So just to wrap up, I want to talk about how there's a number of new tools people can use in studies now. So there's new types of sensors. Sensors have been integrated into these AR, VR displays. There's new data processing capture tools and analytics tools. So for example, Hewlett-Packard have just released the Hewlett-Packard Omnicept VR headset. It has a very wide field of view, high resolution, but the most important thing is that it has heart rate tracking integrated into the VR headset, pupillometry and eye tracking, and also face camera as well. So some of the earlier experiments we did where we had to have people wearing lots of equipment, they don't need to wear that anymore because it's all inside the head mount display. So it's super easy to do the studies. And there are other people like the NextMind who are developing EEG electrodes designed to work with head mount displays. So you don't have to have a brain cap anymore with all the electrodes on it. This is a 9 electrodes that can strap on the back of the VR headset. And this video here shows it working. So the person basically can look around, and as they concentrate, they can send out these kind of virtual waves to destroy these aliens. So it's measuring basically the alpha activity of the brain. And there's also tools you can use as well. You know, obviously when you're capturing all these other types of data in VR, it's quite difficult to analyze the data. So the companies have produced a range of tools. One of them is a company called Cognitive 3D, and they basically have built, you know, on the web, there's lots of web analytics tools for measuring people's activity in terms of where they're clicking and browsing on the web. So they built the same thing for VR. So you can see on the right-hand side a heat map showing where the person's been looking and interacting with. Here's a video of this working. And in this video, you're going to see a person who's in a virtual grocery store, and he's supposed to be selecting products in the grocery store. So you can see the VR view there. He's using his controllers to pick up products. But what the Cognitive 3D does is it produces a heat map of people's activity and what they're looking at, what they're touching. And then once you've run a user study with 20 or 30 people, you can then aggregate all that together and find out what's the most common objects people select or look at. So it makes it much easier for the experiment designer rather than having to process all this data by hand like we had to do with some of our earlier studies. So you can see the person looking through there, and I'm just going to fast forward a little bit. So this is the output. So in this case, they can select what objects interested in. So interested in this, I guess, face cream bottle. So they can now look at how many people looked at that face cream bottle out of all the user subjects, where the bottle was placed and how that affected viewpoint and things like that. So just to finish up, I want to talk about how important it is to move beyond questionnaires. So when I first started user studies in AR and VR, obviously we had these very simple questionnaires, but now we can move from using questionnaires after the experience to capturing data from during the experience. So moving away from performance measures to more process measures. And there's a wide range of rich data types you can capture, as I've shown, using EEG or GSR or behavioral cues. You can also use that to map to high-level understanding, so map to cognitive load or emotion recognition, and there's a lot better analysis tools as well. There's also a lot of opportunities for research. As I showed from our meta review, there's really a need for increased studies in collaboration in particular, but there's also a need for more use of field studies. You know, what do people do when they're using AR devices out in the real world? And having a more diverse selection of participants. You don't just want to have university students, but how do elderly or people with different ability interact with VR? We need a wider range of evaluation measures and also look at the correlations between objective and subjective measures. And finally, we need better tools. As I've shown, there's some huge physiological sensors that have been built into head mount displays, but there could be a wider range of sensors. And there's definitely a need for new analytics. It takes a huge amount of time to process these EEG experiments because they generate a massive amount of data. So we need new tools to be able to process that very quickly and obviously the physiological cues as well. So just to conclude, most AR VR studies are quite limited. In fact, as we saw from the meta review, only about 10% of AR papers even have a user study, and mostly they're lab-based with very simple qualitative or quantitative measures. But there's new opportunities for much richer data collection, moving from post-experiment collection through during the experiment and a wide range of sensors and analytics, and also lots of directions for future research around how to do better user studies. So that's pretty much what I want to talk about today. Thank you for your time, and I'm happy to answer some questions if you like. And of course, these slides and the video are going to be made available later on as well.
Thank you very much, Mark. If anybody has questions, you can either use the icons at the bottom to raise your hand or just unmute yourself and ask a question to Mark.
Mark, might I start?
Of course, Holger.
I'm turning on my video. Sorry.
Yeah, definitely.
Thanks, Mark. Very nice talk. Also, very nice overview. You know, how can we measure things and what is the future direction here also for our students? I would like to. I have a question about the presence measures, of course.
Yes.
So in all of those scenarios, actually, were all stressful scenarios, right?
Yes.
So either really provoked stress, like with the pit, or even with the cognitive load, it has that stress element, right? I have more elements to select. So what are we actually measuring here? Are we measuring presence, or are we measuring simply stress or cognitive load, right? And that's a little bit of yeah. I'll leave that to you to answer.
Well, that's a great question. So I guess it's hard. I mean, and of course, you're an expert on presence measures yourself. Certainly, in these experiments, we are seeing a correlation between some physiological measures and some subjective measures of presence. Whether or not that means, I mean, the hope is that those physiological cues can be used as a more objective measure for presence, but they're also measuring something else that correlates to presence. So as you said, it could be stress that actually, as you're in a highly stressful environment, you may feel more present. But actually, in the research that Arindam's going to talk about in a couple of weeks, the VR environments that we used there weren't, well, they're arranged. Some were stressful, some were not. Some were very calming VR environments. So there is a range of studies that have found that you can use EEG for and physiological cues for some measures of presence, even when you aren't in that stressful case as well. But it's super early. So I think it's, I would say, definitely an area that you'd have to do some more active research on. And as you know, of course, yourself, there's still a lot of debate about good subjective measures for presence, let alone good objective measures for presence as well. But it may be that some of the factors that these subjective, these physiological cues are measuring, like emotion, for example, may be a key component of presence. So actually, it may be there's not a direct correlation; it's an indirect correlation like that. But we don't know until we've done more research, basically. So some work for you and your students, I think.
Can I intersect?
Sure, Ewan.
So I come from a healthcare background.
Yes.
And our major issues for practitioners is clinical human factors.
Right.
Situation awareness, fixation error, leadership, followership, communication skills, interpersonal skills, as a whole, and how to work under pressure, which leads to what you've been measuring. Out there in the real world, when we want people to behave under pressure, and they're doing that right now, would be nice to see that we could use AR and VR to prepare them in that environment much more effectively, so that when they do face the reality of dealing with 400,000 COVID patients at once,
right,
they're kind of prepared. I'm being a bit exaggerating there, but just generally, if from a patient safety perspective and a risk mitigation perspective, this field is just wide open, ready for research and translational research.
Yeah, that's part of what we're doing. I didn't talk about it here, but we're looking at also, for example, using AR for remote collaboration, where you might have a clinician in the patient's bedside or in a surgery, and you've got a remote person who's effectively looking through their eyes and providing guidance. If you can measure stress or cognitive load of the person doing the surgery, for example, that might provide an important cue back to the remote expert saying, well, they're very stressed right now. You might want to wait before you give some guidance, or you might want to help calm them down or something like that. But it's very difficult to do those measures in a real world environment. So there's a lot of work needs to be done. But seeing some of those visual sensors getting into the headsets is one example of how the manufacturers now feel confident enough that they can bring them into that into a real world use case scenario. So I think you'll see more of that happening in the next few years around AR and VR displays that have stress and emotion sensing, and then how that can modify people's behaviors, cognitive load behaviors in a real environment.
Yes, we've bought a suit to measure all those biometrics, but we can't do anything because we can't put it on people's bodies.
Oh, okay.
$12,000 suit sitting on a mannequin.
Well, the hope is you can, and we've done some research on looking at what cues are better than others. So basically well, the current approach is take every sensor you can, put it on somebody's body and measure everything and try to figure out what it is. But actually, it might turn out to be that, you know, a heart rate sensor plus eye gaze may be the two ones that.
Yeah, we don't know. We don't know.
So that's where the research part is.
It's called a Tesla suit.
Oh yes, I know Tesla suits. Very expensive. Congratulations on getting one. So, yeah.
It was end of year spend budget.
Oh, okay. I guess it provides haptic feedback as well, doesn't it? So it's
it
pretty,
does.
Yeah. But yeah, it's hard for me to imagine a use case where you want to use it. But anyway.
Well, we'll see.
Yeah, I'm sure you'll come up with something.
Thank you.
Thank you, Arvin, and thank you, Mark, again for the very interesting talk with many different aspects of user studies. Thank you, everyone, for joining. I think we picked at some point at 20 participants today, so that's a great turnout. We will put everything online, and Mark, please send me your slides as a PDF.
And if anybody has any questions after, I'm happy to answer questions over email as well if you want to continue the conversation. So please.
I do.
Great. That'll be good to talk to you more. That'll be great. Yeah. Excellent.
Again, so thank you again, everyone, and we'll see you on Tuesday for Steffi's talk.
Good to see you all. Thanks a lot. Bye.
Yeah, bye-bye.
Thank you, Mark.
Bye.